So we will talk about cross validation. So cross validation is not an algorithm, okay? This is not an algorithm. This is a process which is used to make your algorithms more robust. Okay? We will talk about why are we trying to make our algorithms more robust. Is whatever whatever we have studied, was that not robust? If yes, if no, then why are we trying to make it more robust? So we will see all of that now. Okay. So until now, what is the process we have followed? Whichever algorithm we are trying to run. So let's say we were dealing with supervised learning so far. We saw a few algorithms for regression and then for classification. For regression and classification. For regression, we saw linear regression. For classification, we saw logistic regression. Then we saw decision trees, which can be used for both. So let me write it at both places. And we will see a few more. Okay. And what else did we see? We also saw that what is the process to run an algorithm? We have our data. Okay, we have our data. We divide the data into training and test. We divide the data into train and test. We usually keep a larger portion into train and a smaller portion into test. So we keep around 70% into train and we keep around 30% into test. This is not hard numbers. You can vary it from 60 to 80% and here from 20 to 40%. Okay. So this is what we do. We first build a model on our training data. So what we do is we run this. So y is known to us in our training data, x is known to us in our training data. What is not known is the function f. So since this is known, we try to find the function f here. And then once we have the function f here, we run that function on the new set of x, which comes from the test data. Okay, and then we get our y. This is y hat, the predicted values. Okay, y hat values. And then we compare this y hat with the y actual values to see how much error are we making. Okay, this is the process we follow for all the algorithms. Whichever algorithm you take, we have followed this particular approach. Everybody follows till here? Are you following? This is what you have done for all the algorithms. Now, can somebody tell me if there is something wrong with this particular approach? Do you think everything is okay with this approach, or are we missing something here? What do you think? Are we missing something here when we do this train and test split, and when we build our model on the training data, and then apply that model to predict on the test data, and then compare the predictions with the actual value to find out how good the model is or how bad the model is? Is there something wrong with this approach? So for example, if you run a decision tree, okay, so we have seen a few parameters in decision tree, right? So we have seen the max depth. We saw the max depth parameter, which defined how long will your tree be, basically the depth of the tree. So more the depth, longer is the tree. And then we also saw min samples leaf parameter. Okay, min sample leaves parameter, what was that doing? That was basically deciding the number of data points to go for a further split. So the smaller number you give, more the split. Smaller the number, more the splits. Okay, or I can say in other ways, I can also say that max depth and min sample leaves are inversely related. Right, guys, are you following? because higher value of max depth gives you a longer tree. Okay, but smaller value of min sample leaves gives you a longer tree. So they are inversely proportional. Okay, this one smaller the number, more the splits. This one smaller the number, lesser the splits. Okay, so let me write it down. So I say they are inversely proportional. So what is the process we have followed so far to run a decision tree? Now we don't know the correct values of these. Max depth or min sample leaves is not known to us. So what did I tell you in the last class? I told you that we start with some values. Okay, we start with some, let's say min sample leaves, or let's say max depth. So max depth, what we will do, we will start from 2 and we will go all the way till, let's say, 20. We will try all the numbers, 2, 3, 4. We will try all the numbers, and for each number, so we will do this in a loop, and for each number we will be checking our test accuracy. Okay, also the train accuracy, of course, so that we will know if we are overfitting or not. Okay, so remember those plots that we studied. So remember those plots. So max depth, and this is accuracy. So how would it look like for the training data? Tell me, guys. How would this look like for the training data and then for the test data? Tell me first for the training data. How would this plot look like for the training data? Increasing trend. Okay, yes, that is correct. As the max depth increases, of course the accuracy will keep on increasing because you will go on making more and more splits, and making more and more splits is always good for the training data. Okay, because this is training data, these are the same questions that you are studying for an exam, so of course you will perform well on the same set of questions, right? Training data is the same set of questions which you are learning. It's your question bank. So the more you read the question bank, the better you will perform. You can memorize the question bank if you want. Even then you will perform better. Okay. But the problem comes when you go on the test data, when you go on the actual exam, because there you will have a few questions outside the question bank. Okay. So there, if you have memorized, you may not perform well. So how would it look like for the test data? How will it look like for the test data now? Inverted U. Yes, that is correct. Okay, it will look like an inverted U. So initially it will increase because you are learning more and more, but after some point you have started memorizing the data. You have started capturing the noise in the data. That is the jargon which is used in data science. So till here you are capturing the pattern, but beyond that you have started to capture the noise in the data as well. So you have started to memorize the questions and it is not helping you. You are not getting the concept, but you are starting to memorize. So that is why you will not perform on the actual question set. On the questions which are not from your question bank, you will not perform well on this, and so your accuracy will fall after that. Okay, so this is the area which we want to find. Okay, this is the area where, and always remember, the real test of the model is how it performs on the test data, not on the trained data. Okay, if it was trained data, you would just select a max depth of infinite and you will get the highest accuracy. But if you take infinite or a large number, your test data accuracy is very bad. And the test of the model is on the test data, not on the training data. Okay, so you have to find this region. Now that is why I said that you start calculating the accuracy for all values of max depth starting from 2 to, let's say, 20, and you see how is it varying. You see the pattern. So you cannot do this iteration just for the test data, because if you do just for the test data, it will be difficult. So what you do for the training also. You do for training also, so that you know that you are overfitting. So for example, if you are here, you will know that you have overfit the data, because let's say you will get 80% on test and you will get, let's say, 95% on train. So you will know you have overfit the data. If you don't have the training data accuracy, how will you know? You will just get 80%. So you will not be sure. So that is why we do both for training and test data while we do these iterations. Okay, so while we do these iterations with different values of max depth, we keep checking the train data accuracy, we keep checking the test data accuracy. Okay, and then we try to draw this plot. And then using this plot, you can find out that, okay, my best value of accuracy is coming for a max depth of, let's say, 10. After 10, it has started to fall. So I will use 10 as my final max depth for the final model. Is that clear, guys? We have covered all this in the last class. Is that clear? I will share an assignment and a case study on this very soon. So by in the next couple of days, you will have a assignment, a quiz, other reading materials already from this. Some quizzes I have already shared on this. Yes, it will always be like this, Anupama, because you start capturing the pattern, and after that you start to memorize the data. So it will always look like this. Okay. Now, what I may not know is where this point will come. Where will I get the best accuracy? That may not be known. But the curve will always be like this. Okay, it will always be like this. It may start from, let's say it may start from 2 and go all the way till 50. And the best point may come at 30. Okay, or it may start at, let's say, 1, and at 5 itself it might end and the best point might come at 3. But the pattern will always be like this. The trend will always be like this. These points will keep on changing. Okay, that is what you have to find with respect to the particular data. This will change based on the data. Okay. Now it may not be exactly like this. I have smoothened the curve. It might be like this actually. It might have ups and downs. Even while going through the trend, it might have ups and downs, but I have smoothened it. Okay, so if you draw this on actual data, you will see it is very unstable. It will keep going like this, like this, like this. Okay, but if you see the overall trend, it will be an inverted U. Okay. Did I answer your question, Anupama? Okay. Now we are starting to go towards cross validation. Okay. Now there is one big problem with this approach. Now this approach is quite good and it is very popularly used, but there is one small problem or other big problem with this approach. Now what is that problem? Do you see that problem, guys? It's a little difficult to catch, but there is one basic problem to this particular approach. Can anybody guess what is that problem? Selection of data. Okay, what about selection of data? Can you elaborate? Naresh, you are not doing any iteration of testing by interchanging data proportion of training and test. Your training and test, you are not changing it. It is still the same. So these 70% is in training, this is in test. You're not changing that. Okay. So we are not doing what you have just written. Anupama says if we select similar pattern records in train. That is a problem. So Anupama, we are doing a random split. That is why we do a random split. Okay, we never divide the data as the top 70% going in train and the bottom 30% going in test. We always do a random split. And when you do a random split, usually that doesn't happen. That similar pattern records go in train and something different goes in test. That does not happen because you are doing a random split, totally random. So it will select random rows and random rows into train and other random rows into test. So that will never happen if you are doing a random split. Okay, so that is not the issue. Okay, I'll tell you what the issue is. Okay, now what are we doing here? We are looking, we are so one basic concept which I told you at the very beginning when we learned about splitting the data into train and test. Test is like your actual exam, right, guys? Test is like your actual exam. Your test should be totally isolated. The test data should be totally isolated from model building or model training. While training the model, you should not have any idea about your test data. If that happens, that is like cheating. Okay, so that is like you already know what questions are going to come in the exam and you are training based on that. Okay, you are going there and looking what questions are coming back and learning that type of question. Again going back, looking at what type of questions are coming, and then again coming back and learning. This is similar to what we are doing here, right? We are looking at which value of max depth is my test data accuracy the best, right? That is what we are doing. So let's say at 4 it is not best. So how did we know that our test data accuracy is not best at 4? Because we went to the test data and saw its accuracy there, and we realized that it is not good. Then we came back and we did at 5. Then we came back and did at 6. So we did at all these numbers and then we realized that okay, at 10 it is the best. So this is like cheating, right? Because we are going into the test data, looking at what the accuracy is and then coming back and then again changing the numbers. Do you understand, guys? We are going to the test data, looking at what the accuracy is and then coming back. So this is like cheating, looking at the actual test that we would be appearing in and then coming back and preparing accordingly. Or let's say it is also like you can say that going and writing some answers to questions in the exam, and once you get the marks for those questions you see that you have not gotten a good marks, so you go back, learn again and then rewrite the question, which never happens, right? It is like retaking exams again and again. Okay, changing your answers. So you give some answer, it doesn't give you good marks, so you change your answer again. This is similar to what we are doing here because we are changing the value of max depth based on the accuracy on the test data. But this is wrong, right? We should not be allowed to do this. Your test data should be totally isolated. Your test data is how your model will perform in the future. Now, in the future, you will never know what the actual value is. So you will not have an option to compare your prediction with the actual value. So your prediction should be totally independent of how the data is in the test data. It should not change based on the value of test data. Do you follow, guys? Let me give you another example. If that was not clear, let me give you another example. Let's talk about let's talk about the Indian Army. Okay? Let's talk about the Indian Army. So the Indian Army, just a minute, guys. Sorry guys, I had gotten a call. Yeah. So let me give you another example to explain it. Okay, this is a very important concept, guys. So make sure you understand, even if it requires me to repeat this 10 times. But make sure you understand. I will also share some videos which I have pre-recorded. I will share that on the LMS, so that will also help you understand it. But think of it from a sit down when you are at peace and when you are alone, when there is no disturbance around, and think of this is very logical. It is very difficult to understand, but it is logical. Okay, so let's talk about the Indian Army. So the Indian Army is trained to fight on any terrain, right? Of course, the army of any country is trained to fight on any terrain. Okay, so they are trained to fight in forest, they are trained to fight in the desert, they are trained to fight in water, be it ship, river. They are trained to fight in mountains, and what else? And whatever it is, whatever else you see, okay? So they are trained to fight everywhere, okay? Now, let's say this is your training data. The Indian Army is getting trained to fight at all these places, okay? Now, let's say we have a war situation. We have a war situation. Now the war will not happen on all these parts, on all these terrain. It might happen in maybe one or two terrain. So let's say we take desert for example. So let's say we are having a war on our northern border. Let's say maybe towards Rajasthan. Okay, like we had in 19. Okay, I don't know which year it was. We have had three wars. Okay, so let's say we had it in. We are having a war on a desert now. Now the Indian Army has to perform well on this desert. Okay, now the Indian Army is trained for all these terrains. Okay, now what if what if the Indian Army was not so good on the now if you just look at the accuracy on the training data. Now let's say Indian Army is not so good, here we are not so good. Okay, at all other places we are best, we are best. Okay, but maybe here only we are not so good. Okay, now what would happen as a result of this? Now we will fail here, we may not do so good here, we will fail here, because this was the only place where we did not, where we were not so good. Okay, we were not so good at only this place. So if we check the accuracy only on this place, we may not be so good. Okay, I think I should go back to the previous example. This example I will use again. This is a little more complex to understand. Okay, so let me give you another example. Let me go back to the same example. We are trying to understand the concept of cross validation. Okay, so to understand the process of cross validation, first I'm trying to explain why just train and test is not good. Okay, why the training and test only having these two splits is not good? Because let's say you have 70% data here, you have 30% data here. Now you try, let's say I'm trying different values of max depth. I'm trying values of max that, again I'm going back to the same example because this is the easiest to understand. I'm trying different values of max depth from 2 to 30. Okay, I don't know which is the best value. So for which value of max depth is my test data accuracy the best? I don't know that. So how will I know that? I will use each of these values iteratively. So first I will use 2 as the max depth, and then I will go to my test data and see how is the performance. Right, this is what I will do. Then I will take 3 as my max depth, go to the test data and see what is the accuracy for depth 3, and so on till 30. So I will have the accuracy, I will have the train accuracy, I will have the test accuracy. So let's say this is accuracy. Okay, for max depth of 2 till 30 I will have these numbers. Okay, and then I will see for which for which of these is my test data accuracy the best, and then I'll finally select that corresponding max depth, and I will finalize the model. So my final model, because my final model can have only one max depth, it cannot have 10 different max depth, right? You can only build one function f of x. You cannot build 10 functions, you just have one function. So one function means it should have only one value of max depth, it cannot have different values of max depth. But to find out what is that best value of max depth, you will have to do these iterations. You will have to do these iterations to find the best value of max depth, and once you have figured that out, you will finalize your model, let's say f of x, which will have that best value of max depth. Okay, all clear till now? All clear till now, guys? Okay, now what is the problem here? The problem here is that we are going and looking into the test data. We are going and looking into the test data and then deciding what is the best value of max depth, which should not happen, which is like going to the exam, looking at the questions, and then deciding that, okay, I will study like this. You will not be allowed to do that. Do you follow? You will not be allowed to go to the exam, look at the questions, and then come back and change your mode of preparation. That never happens. So even before going to the exam, you will have to do that. You will have to decide your preparation strategy, which questions you will learn, how much of which topic will you learn. You will decide that before going to the exam. Test data is your exam, always remember. You cannot go to the exam and you cannot decide what is the best value. Okay, so this is a strategic error, I would say. This is an error in the strategy, which is not allowed. This cannot happen. Okay, do you understand why this is wrong? Yes, any questions? Do you follow why this is wrong? Yes, it is not possible, but you have been doing this, right? You have been doing this. So let's say another example. Let's say I have data from 2010 till 2018. Okay, and you have to make predictions for 2019, right? You have to make predictions for 2019. So what will you do? You will, this is your final test data where you do not have y, where y is not known to you. Okay, so what you will do, you will take 2010 till 2016 as your training, and you will create a test data of your own. So you will create a mock test of your own. So 2017 and 2018 will be your mock test data, which I'm calling test again. This is what you are doing, right? And this is what we studied so far, that this will become your train data and this will become your test data. So this is like your mock test data, or the mock exams that you give. So if you have been a CAT aspirant anytime, you would know that all the coaching institutes like Time, Career Launcher, and whatever, they all have these mock tests. Okay, and these mock tests are a very good indicator of how you would perform in the actual exam, because almost equal number of students take the mock test also. So let's say if 2 lakh students are taking CAT, around 1 lakh 80,000 or 1 lakh 70,000 would be taking the mock tests also. So however you perform on the mock tests is very similar to how you would perform on the actual CAT test also, right? So that is what we do here. We train the model from 2010 to 2016, and then we predict it on these two. Okay, we predict on these 2 years and then check the accuracy. And if we are happy with that accuracy, we finalize the model and then use that model to predict for 2019. Now, how did we perform on 2019? We cannot say that because 2019 is still not here. So we will get to know that only once we are into 2019. So until then, there is no option but to wait. But using this strategy, we can have a very good idea of that. Okay, since this model, whatever model we built here, it performed well on 2017 and 2018, it will very likely perform well on 2019 also, right? This is what we have been doing. So this is the same thing what we have been doing, but I will talk about the flaw in this approach. Okay, so here we have not gone to the test and we have not cheated here. Okay, 2017 2018 is not the actual exam, so the point of cheating that I was talking about is not present here. Okay, but still there is a flaw in this approach. Okay, the flaw, I would talk about the flaw now. What is the flaw in this approach? The flaw in this approach is that we were changing, let's say we are running a decision tree model. Okay, so we have our max depth. Okay, now we change the value of max depth to get the best accuracy for 2017 and 2018. This is what we would do, right? We would try different values of max depth, and whichever gives the best accuracy on, so we will, yeah, I was sneezing. So we would try out different values of max depth here, and whichever max depth gives the best accuracy on 2017 and 2018, we will we will finalize our model based on that particular value of max depth. Okay, now the main problem with this approach is, let's say we finalized max depth of 10. We got a value of 10 as the max depth for 2017 and 2018. Okay, now what if this 10 was only good for 2017 and 18? Maybe this 10 is not good for 2019. It may be possible, right? Maybe for 2019 it is 15 which is the best value. But since we only looked at 2017 and 2018, we got the value as 10. But in 2019, 15 would have been the best value. We do not know that, right? So this is the flaw if we just take a train test split, because we might have a model which performs well just on the test data. It might not perform well in the future, but just on the current test data or just on the mock test, it might perform well. It is like, let's say you are preparing for CAT and you go and give a mock test. Before the actual exam, you go and give the mock test. And maybe whatever you have done, whatever you have studied, only worked on the mock test, but may not work on the test, on the actual test. That also is possible, right? Your way of preparation, maybe it is only particular to how the questions are set by the coaching institute, not by the actual CAT exam. It may be possible. Are you following? So now I can come back to the Indian Army example. Now let's say we are talking, now the war happened in desert. Okay, now your army is well trained on almost all terrain except one. Except one terrain, it has performed well on all other terrains. But you want your army to be well trained on all terrains, but on the desert it fails. So that may cost us very dearly, right? If it fails on the desert, right? So that is the problem with this approach, that maybe your way of preparing the model only performs good on one particular kind of test data, or only performs bad on one particular kind of data. Okay, so let me give you another example. This is your train and this is your test, and this is your final test data. This is your final test. This is like your mock test. Okay, this is also known as validation, by the way. The mock test that we are talking about is also known as validation data. So sometimes you will see people will split their data into train, validation, and then test. So three splits they will make just to avoid that cheating thing. We talked about cheating, right? So what they will do, they will they will decide the max depth based on the best accuracy on validation data, and based on this they will freeze the model, and then that model they will use to test on the final test data. So here there is no cheating. This is like a mock test. Okay, so you prepare, and based on what preparation style is giving you the best accuracy or best score on the mock test, you finalize your preparation strategy, and then you use that strategy to perform on the test data. So here there is no cheating because you are not going to the test data and coming back. Okay, you're not going to the test data and you are coming back. So it's like, let's say you have 1, 2, and 3 strategy. So first is learning 5 hours per week. Second is, let's say, 8 hours per week. And third is, let's say, 10 hours per week. Three strategy you have. You try all these strategy on the mock test. Okay, on the mock test. And let's say this strategy worked the best on the mock test. Here maybe you were over exhausted and you did not do well. Here you were not performing enough. This probably is the best one. So you see that if I try 8 hours every week, if I study 8 hours every week, I am getting the best accuracy on mock test. So you finalize this, you take this strategy, and then using this strategy you finally predict on the test data. You finally go and write the test, the actual test. So here you're not looking at the test data and coming back. You're doing that on the mock test, not on the actual test, right guys? You're only looking at your mock test and trying different strategy. So 5 hours, let's say you are getting 70% marks. 8 hours you are getting 85% marks. 10 hours you are getting 80% marks. So you are only looking at these marks on the mock test, not on the actual test. Actual test you have no idea. So looking at your performance on the mock test, you have realized that 8 hours every week is the best approach. So you will use that approach on the final test. Okay, do you follow this? So that is why you will see a lot of people divide data into train, validation, and then test. So they divide it into 3 parts, not 2 parts, to avoid that cheating thing. Do you follow? Do you follow, guys? But this approach also has the same problem. What if this 8 hour strategy, what if this is good only for mock test? Maybe this 10 hour was good for test. We don't know, right? We just assumed that 8 hour every week is good for mock test, so it will probably be good for the actual test also. We assume this, right? This may not be true. Maybe 10 hour every week is only good for test. So we don't know. So there you run a risk of making this problem. You run a risk of doing this problem. So coming to the Indian Army example, you cannot just looking at the performance of the army on the desert, just looking at the performance of the army on the desert, you cannot say that your army is good or your army is bad. Okay, because this is just one terrain. If you want to, so let's say this is a mock war. This is a mock war. Okay, so just looking at how your army performs on one terrain, you cannot say that your army is good or your army is bad. Okay, you will have to evaluate it on all the terrains. Only then you can be sure. Or let's say your army is too good, maybe not so good, not so good on the other terrains, not so good. Okay, so it is not so good on the other terrains, it is only good in desert, and you tested their skills only on the desert. So you might feel that your army is the best in the world, but this is the only thing where they are good at. right? This is the only thing where they are good at. So you should not take a judgment based on just one value of one value in the test data. Okay, so what should we do to avoid this? So the point I'm trying to make is you should not just look at the mock test data. Okay, you should not just look at the test data and decide that this is the best value I should take in my model. So just looking at the test data, you should not decide your max depth or min sample sleeve, because that value might only be good for that particular test data. It might not be good for some other test data. Okay, so how should we avoid this? What do you think? What do you think? What is the way to avoid this? Are you getting the problem, guys? Did you understand the problem? Yeah, we will talk about this. Why are we talking about cross validation now? There is a reason for that, Sinoj. Okay, I'll talk about that reason towards the end of the class. Why are we talking about cross validation now? Why did we not talk about this during linear regression or during logistic regression? Why are we talking about it in cart? Okay, we will see that. Just remind me this. Remind me this question before we leave for today. Okay. But how do you think we should address this problem? So the problem that we are facing is that if we just look at the test data and decide our parameter values, this becomes cheating because we are looking at the test and then deciding the parameter value. So to avoid that, what we will do, we will divide our data into train, validation, and then test. That way we will avoid the cheating part. But even if we do that, we might still fall into trouble, because whatever values we come to, whatever parameter values we finalize, that might be good only for the validation data. That might not be good for the actual test data also. So how should we overcome this problem? Guys, what do you think? What do you think can be done to avoid? But Shinoj, if you do that, that will again become cheating. That will be like going to the actual test and looking at the questions. Okay, so let me explain. This would be difficult for you because this is something new. So let me explain how can this be done. Okay, so a quick recap. I'll just revise everything that we have seen so far. Okay, so what is the problem we are facing? So let's say, let me give you a fresh example. Okay, I'll give you a fresh example. So if you haven't understood so far, please pay attention now. Let's say, you are preparing for an exam. Okay, so I will take my training data. My training data will be all the concepts that I need to learn for exam. So let's say algebra. I have algebra. Then let's say I have trigonometry. Okay. Then I have, let's say, what else? What else are the topics in mathematics? Let's say uh, calculus. Yes. What else? Give me some more topics, two, three more topics. Derivatives that comes under calculus itself. I think broadly, if we see, this is, let me write some other, let's say computer science. Okay. Let me write all the subjects that are. Okay. So let's say these are the topics that you are preparing on. Okay. And let's take our first approach. This is our first approach that we have been taking so far, where we divide our data into just training and test, right? We divide our data into just training and test. And let's say I have my test data also. I have my test data, which has, it will not have all the topics, it will have a few topics. So let's say I have calculus, I have physics. I have only these two topics. Okay. So what you will do is you will prepare on all of these. You will prepare on all of these, and then you will check what accuracy are you getting on, let's say, calculus, on physics. Okay. Now you will change your style. What you will do is you will focus more on calculus and more on, sorry, computer science, not computer science, physics. You will focus only on calculus and only on physics, because that is what is coming in the exam. This is what any person would do, right? If you already know that only calculus and physics is coming in the exam, you will only prepare for calculus and physics. Why would you prepare for the other stuff? Okay, you will not prepare for the other stuff. Okay, so this is wrong, right? Because you went to the exam and you saw what was coming in the exam, and then you came back and changed your style. So that is why this is totally wrong. So dividing your data into train and test alone is wrong. So whatever we have been doing so far was not the best approach. It is totally flawed. Okay, that was a flawed approach. Okay, so to avoid that, what we will do, we will prepare a mock test. We will prepare a mock test which we will call validation. Okay, which we will call the validation data, and that will also have some subjects. Okay, and we will have some test also finally. So we don't know what is going to come here. We don't know what is going to come here. We will prepare some validation data, and here we will take some similarly we will take some random data points from here. So now let's say we get computer science and we get, let's say, English. Okay, we get these two here. Now again the same problem arises. You will go back and you will study only these two. You will not study anything else. But in the final test you may not have these two. You might have something else also. You might have, I'm saying, I'm not saying you will have, you may have computer science also, but you may have something else also. So again, this is also flawed. Though you have divided into 3 parts, this is still not the best approach, because you will prepare only for computer science and only for English. You will not prepare for the other subjects, and so you will not perform well on the test data, because your knowledge will be limited to computer science and English, not to other subjects, which is wrong. Okay, so what we will do, what is cross validation, I'll tell you now. Now this is what is done in cross validation, which you will understand why this is such a good approach. Okay, so I still have the same training data. Okay, I still have all the subjects that I mentioned here. I will just prepare one validation data. Okay, here also we will have 3 parts. Okay, or I will just have 2 parts only. Let me call it this way. I'll have 2 parts as we discussed before. I'll have training, I'll have test. Okay, so let's say I have all the subjects in my training, and I have, let's say, English and physics in my test. Okay, I have only these two in my test. Now I'm not supposed to go there and see what is coming in my test. So what I will do, from the training itself, I will take 1/3 of the data, or let me explain you. So cross validation, let me explain you the first approach in cross validation, which is, so the first approach in cross validation is leave one out cross validation. Okay, this is known as leave one out cross validation. Now, what is this leave one out cross validation? Let me explain. So we have your training data. What did we have here? We had calculus, we had geometry, we had physics, we had chemistry, we had English, we had algebra, etc. Okay, this is my training data. So in leave one out cross validation, what I will do is I will take one data point out as my test data. Okay, I will take just one data point out. Let's say I will take calculus out. Okay, now I will build my model looking at this. I will look at the accuracy in the test data, and I will build my model. So my model will perform good on calculus, right guys? Since I have already built my model as per calculus, my model will perform good on calculus. But again, this has the same issue, because it might not perform well on the other topics. So what I will do, I will repeat this process. This is iteration number 1. Now iteration number 2 will start, where I will check the model's accuracy on geometry. Okay, and then again it will repeat. Then once again I will check the model's accuracy on physics. Once again it will repeat. I'll check the model's accuracy on chemistry, and so on till the end. So I will check the model's accuracy on all the rows, on all the concepts, on all these concepts. I'll repeat this process multiple times. So whatever we were doing earlier, it is very similar to that, but earlier we were just checking for one set of test data. Here what I will do, I will check for every row. Every row present in my data, I will check how is the model performing on each of those rows in the data. Do you follow? So I will prepare on all these topics, and then I will see how am I performing on calculus. Then I will see how am I performing on geometry. Then I will see how am I performing on physics, chemistry, and everything. This is what you actually do when you prepare for an exam, right? You test yourself on all the skills. So that is what is leave one out cross validation. Why leave one out cross validation? Because you are leaving one row out. These are all rows. Okay, I'm talking about these are all rows. So you're leaving one row out, and then you are checking whether your model is performing good on that particular row or not. Okay, so this is what you are doing. Do you follow, guys? So this is helpful, because so we are not doing any. So why this is a better approach? This is a better approach because, and always remember, this is still your training data. Okay, this is still your training. From the training data itself, you are looking like this. Your actual test data is still separate. You're not looking into the actual test data. This is like a dummy test data that you have created. Okay, so you are not doing any cheating because you did not go to the actual test data to see how are you performing. There is no point of random state here, Sinoj, because you are looking at every row. So every row will come one at a time. It is not random. It is one by one. It is not random. It is one by one. So every row should come here in the test data. Okay. So if you have, let's say, row number 1, 2, 3 till n, then you will build your model on all of these. You will test your model on the first row. Then you will test your model on the second row. You will test your model on the third row. And you will test your model on the nth row. It will go on like this. So how many times will your model run? Can you tell me? How many times will your model run in this case? N times, yes. Where n is the number of rows. Your model will run n times in that case. Okay. So this is the best approach that you can check. So that you can have. So this is like, again, I will bring the Indian Army example here. Your army is trained on, let's say, 5 terrains. You test your army on the first terrain, then you test your army on the second terrain, you test your army on the third terrain, fourth terrain, and fifth terrain, and then you find out the accuracy. You calculate the accuracy, so you will get accuracies at every place, right? So let's say you get A1, A2, A3, and you will get AN. So your final model accuracy is average of all of them, summation of AI divided by N. Okay, your final accuracy is the average of all of them. So you test your army on all the terrains, and then you evaluate how good or how bad is your army, because you have evaluated the army on all different terrains. So now you can be sure whether your army is overall good or not. Do you follow? This is why leave one out cross validation is a very good approach, which removes all disadvantage of just having a train and a test data. Because when you have just a test data, or when you have just a test data, you are cheating. You are looking at the answer and then changing your strategy, which is wrong. Okay. Now to avoid that, you will have three sets of data: one train, one validation, and then one test. But again, that is also wrong, because your model might be good only for that particular validation data. It might not be good in general. It might be good only for a particular set of test data. It is like, you are checking your army's skill only on one terrain, let's say desert. So if your army is very good in desert, you will think that your army is very good everywhere else. Or if your army is very bad on desert, you might feel that your army is overall very bad. But maybe that is one exception point. Maybe that is outlier in your data. Okay, so that validation set might be an outlier. So you cannot take a decision just based on an outlier. You have to take a decision overall. So that is what leave one out cross validation does. It checks your model's accuracy on every row, so on all possible rows. So you have evaluated your model on every data point. So whatever you get out of this is the best. This is the best that you can do. Okay, and every time you are doing this, you are retraining your model. Okay, you are retraining your model. So when you check on the first row, you find out some value of let's say max depth. We are talking about max depth, let's say. So let's say you check your model's accuracy on the first row, and you find the best value of max depth. Let's say it is 2. Then on the second row, again you check the best value of max depth, and so on. You keep doing this. Okay, so let me open a new page. Yes, we will talk about that, Naren. Naresh, we will talk about that. That is why this is not the only approach to cross validation. There is one more, and that is more commonly used, because there is one drawback to this, as Naresh has highlighted. We will talk about this. So leave one out cross validation is not used because of the drawback that you have just mentioned. Because it takes a hit on performance because your model runs n time. Let's say if you have 1 lakh rows, your model will run 1 lakh times. So imagine how much time will that take. So this is not used. But it is good to understand because this is the best approach you can take. Okay. So let's talk about max depth. Okay. So you have your training data. Okay, you have some test data. Forget about this test data. I don't even know what the test data is. Okay, I'm not even looking at that. It is totally isolated. So my training data has n rows. So what I will do, I will use 1 to n minus 1 rows. Okay, to train my model. To train my model, and the last row which remains, that will be my dummy test data. Okay, so forget about this test data. I'm talking about a smaller dummy test data, or the validation data, you can say. Okay, so I will build my model on all but the last row, and the last row is my test data. I've taken the last row as my test data. Okay, and then let's say I decide my max depth parameter. I decide what is the best value of max depth. Now what I will do, I will go from 1 to n except n minus 1. So n minus 1 is not taken here. That n minus 1th row will come here. That will be my test data. And once again, I will find my max depth. Okay. And this process will repeat. At the last, you will see that it will start from 2 to n. 2 to n will be my train, and my test data will have the first row. And again, I will calculate the value of max depth. Okay, so how many values of max depth I will get? I will get n values of max depth. N values of max depth is what I will get. Okay, but finally I have to take one particular value of max depth, right? I cannot take n values of max depth because finally I have to build one model which I will use on the final test data. So what is that value of n? Which value of n should I take? Because I have gotten n different values. So what do you think will I take, guys? I will take the average. I will take the average value of n. Yes, I will take the average value of n because that will in general perform well overall. Okay, overall, so we are, because we don't know what we will get in our test data, right? Will we get the nth row or n minus 1th row or the first row? We don't know. So we will try to build a very generic model. We will not try to build a specific model which performs good only on some particular data. We will try to build a model which is generically well, which performs well in general, so that whatever kind of data you get, it performs well. Okay, so that is why we will take the average value of n, and probably on that average it will perform best on the test data. So this is the best approach that you can take. Okay, there is no other better approach than this, then leave one out cross validation. And that is why it is called leave one out cross validation, because you are leaving one data point out. Every time you run a model, you are leaving one data point out, and then you are running the model. Okay, but of course this has a very big flaw. The biggest flaw is that it is very slow because you have to run your model n times. So if you have 1 lakh rows, your model will run 1 lakh times, and so it will take months to complete. If you have 1 lakh rows, you are building a complex model, it will take 1 month time to complete. And remember, in each run also you are trying different values of max depth. So how did you know what is the best value of max depth? this best value of max depth you can only know if you try different values of max depth. So in every iteration you have multiple iteration with different values of max depth, let's say 2 to 20. Okay, so 2 to 20 you are trying different values of max depth in every of these iterations. So it is actually not n times, it is more than n times that you are running. Okay, very long time to run, and that is why this approach is also though very good approach, but it is not practical. You cannot take this approach because it is too slow. Okay, so that is where we will see which is the most popular cross validation technique and which is very widely used, k-fold cross validation. We will see this after the break. Okay, so any questions so far? Did you follow, guys, why just dividing the data into train and test is not the best idea? And even to remove that, we can take train, validation, and then test, but that is also not a good idea because your model becomes specific. It performs well only on a particular set of data. It may not be generic. Okay, do you follow, guys? Okay, let's continue, guys. So we have seen what leave one out cross validation is. Leave one out cross validation, as the name suggests. Here, what do? We train the model on n minus 1 rows, and the last row is used for testing the model. And this process repeats until each row has become the testing data. Okay, so that means the process repeats n times. Okay, the only disadvantage of leave one out cross validation is that it takes a lot of time to run because you are running the model so many times, n times. Okay, but the advantage is great actually, because the model that you finally build is a very robust model which will perform well on all kinds of data, since the model has been trained on all kinds of data and the model has been tested on all kinds of data. Right, guys, did you understand what I said in that sentence? The model has been trained in all kinds of data and the model has been tested in all kinds of data. Okay, because one by one you are using all the rows to train the model, and one by one you are using all the rows to also test your model. So it's a very robust model, but the disadvantage is it takes a lot of time. Okay, so what is the alternative to that? The alternative to that is k-fold cross validation. Okay, the alternative is k-fold cross validation. So this is also very intuitive. Okay, this is also very intuitive and a very intuitive remedy to the problem which leave one out cross validation has. Okay, so let's see what this is. So let's say this is our training data and you have some test data which I'm not even considering. So we are not looking into the test data, we are not doing any kind of cheating, so this will be isolated. So this is isolated, this is my training data. Now what will I do? I will divide the data into k parts, where k is some number that you select. So let me select 5. K is equal to 5. That means I will divide my training data into 5 parts. So let me do that. Okay, so I have divided my data into 5 parts. Okay, now what would I do? I will train my model on the first 4 part. So 1, 2, 3, 4. And I will create a mock test. Forget about this test. I'll create a test data which will have the 5th part. Okay. So this fold is nothing but part. K part cross validation. So I will train the model on the first 4 part and I will check the accuracy on the 5th part. Okay. And I will repeat this process. So the next I'll take 2, 3, 4, 5 and I'll test the model on the first part. Then I will take 1, 2, 4, 5, test the model on the third part. 1, 3, 4, 5, I'll test the model on the second part. And then finally 1, 2, 3, 5, test the model on the fourth part. Okay, so here how many times am I running the model? I am running it only 5 times. Okay, I am running it only 5 times. And does it still have the advantage of leave one out cross validation? I would say yes, because once again, if you see overall, if you see, you are building the model on all the data, and you are also testing the model on all the data, because your model is being tested on fifth part, first parts, third part, second part, and fourth part, all the parts. And your model is being trained also on all the parts. So all the data is being used to train the model, all the data is being used to test the model also. Okay, and the advantage is that it runs only 5 times, it does not run n times. N is the number of rows. Okay, so this is the advantage of k-fold cross validation. And what do you do after this? After this you do the same thing. So let's say we are talking about max depth. Okay, so max depth on the test data. Let me draw max depth on the test data. So let's say this is how it looks like for the first model. This is the first model. Okay, now let's say it looks like this for the second model. This is the second one. And similarly, let's say for the third one, it looks like this. This is the third one, and so on till the fifth one. So I'll have 5 different curves here. Since I am building 5 models, I will have 5 different values of max depth to select. Now finally, what will I select? Of course, we will select the average here also. So I will draw an average line here. Okay, I will draw a average line here. It will look something like this. And then based on the average, I will select the best value of max depth. Okay, based on the average, I will select the best value of max depth, and my final model will, I'll have the final model ready by taking this best value of max depth. Oh, okay, I had paused the screen. You should have told me before. I have explained everything. Okay, so let me repeat, guys. Let me repeat. Now you can see the screen. Okay, so I was okay. No, I had paused the screen before the break, and I forgot to unpause it. Okay, sorry about that, guys. Okay, so we were talking about k-fold cross validation. In k-fold cross validation, what do we do? I have kept my test data separate, so this is totally isolated. From my training data, I will divide the data into k folds or k parts. Okay, let's say I'm taking k is equal to 5. So I have divided my data into 5 parts here. So these are the 5 parts, all equal parts. Okay, so this has, let's say, 10 rows. This also has 10 rows. Each of them, they have 10 rows. Okay, I've divided my data into 5 parts. Now what am I doing? I'm taking the first 4 parts to build a model and testing it on the fifth part. Okay, testing it on the fifth part. Similarly, I'm building the model again on some other 4 part and testing it on the other fifth part, and so on until all the part becomes the testing data. Okay, so finally you will have a model which is being built on all the parts, and you will also have a model which is being tested on all the parts. Okay, and for each of these 5 models, you will build a total of 5 models. Okay, for each of the 5 model, you will have you will have a plot like this, which will give you the value of max depth. Okay, which will give you the value of max depth. Now the overall max depth, now let's say some value of max depth will be best for this model, some other value of max depth will be best for the second model, and so on. So what max depth will you select? You will select the average, of course. So you will draw average line like this, and based on that average line, you will identify which is the best value of max depth to select, and based on that max depth, you will finalize your model. So now the advantage of this k-fold cross validation is you're using all the data to build your model, you're using all the data to test your model. And the disadvantage which we saw earlier in leave one out cross validation, which was that the model was running a lot number of times, that is gone here because the model runs only k times. Okay, do you follow now? Any questions? Correct, Anupama. So the same part from the training data is being considered as the test. You have a separate test data also, which is totally isolated. So once you have finalized your model, then you take that model to your test data, not before that. Okay. So you're not doing any cheating by looking at the test data and then changing your model. You're not doing that. So it is called k-fold cross validation. We usually take k value of 5 or 10. Okay. There is no confusion here. You can, if your data is very big, you take 10. If your data is not very big, you take 5. Now, what if I take k is equal to n? What would happen? Can somebody tell me? If I take k is equal to n, what would happen? Exactly. Very good, Naresh. Yeah. It will become the same as leave one out cross validation. Okay. So we usually take k as a small number, 5 or 10. Because if we take as a very large number, it will be similar to leave one out cross validation. The model will run so many times and it will take a lot of time to run. So to avoid that, we only take 5 or 10. Okay, so this is all about k-fold cross validation or entire cross validation. Okay, now coming to the question which I think Sinoj asked, why are we talking about cross validation now? Now while we are doing cart, while we are doing classification and regression trees, why are we talking about cross validation? Why did we not talk about this during linear regression or logistic regression? So the answer to that, there is an answer to that. So did you see any parameter which you had to change in linear or logistic? Did you see any parameter which you were changing? Like we have max depth here, we saw max depth here, we saw min samples leaf. We did not see any such parameter there. So there is no need to do cross validation. Usually there is no need to do cross validation in linear or logistic regression models. Why? Because this is only applicable to high variance models. Remember high bias, high variance we discussed. Decision tree is a high variance model, which means it is very unstable. The moment you change your data, the model changes. The moment you change a few rows in your data, the model will change drastically. Okay. So that is why, to avoid all of that, we try to reduce the variance by doing cross validation. Because the moment your test data changes, the model will change a lot. Okay, so to avoid that, because we want, see, our goal in machine learning is to build a model which is very robust. By robust I mean very generic, which performs well on all kinds of data, because you don't know what questions you will get in exam, so you will try to prepare all the topics well. Okay, and instead of focusing on only a few topics, you will focus on all the topics. That is what is called generic, which perform well in all situations. Now linear and logistic regression, they are not high variance model, they are very stable models. They don't change a lot if your data partially changes. But decision trees or decision tree, or later you will see support vector machines, these are high variance models. They change a lot because they can take any complex shape. Linear regression will always be a line, so it will not change if a few points change. So let's say if you have these points, you will get this line. Now even if you add a few extra points, let's say I add extra points here, I add extra points here, your line will still remain probably the same. It will not change a lot. It will still be the same. Maybe something like this will happen. The line remains the same. So this is not a high variance model. Okay. But if you talk about decision trees or any complex model which can take non-linear shape. So let's say this is a high variance model. This is a high variance model. Now in such a model which is non-linear, if you add a few points, let's say I add a few points here. If I add a few points, the model will not stay the same. The model will change. The model will change. So decision tree is such a model. It is a high variance model which changes a lot with the data. So we don't know what kind of data we will receive in the test data. So we try to build a very generic model, and to build a very generic or a robust model, we use cross validation. Whereas linear regression or logistic regression by nature are stable. So there is no specific need of cross validation there, because they are parametric model which always take a particular shape. So they are pretty much stable. But still you will find sometimes people do cross validation there also. There is no harm in not doing, but there is no particular need of it. Okay. And more specifically, there are no parameters that you have to vary. There are no major parameters in linear and logistic which you have to find the best value for. But in decision tree, you have max depth, you have min sample leaves. So you don't know which parameter is the best. So if you don't do cross validation, if you just do it based on a test data set, you will just decide based on a sample of data that what is the best model. But that decision may not be very generic. That might be best only for that particular sample of data. It might not be best for everybody. Okay. So to build a generic model, to build a very robust model which performs well on all kinds of data or most kinds of data, we do cross validation. Of course, if your data totally changes, then you cannot do well even if you do cross validation. So let's say you are learning all concepts of maths and going to the exam, and you realize that today is chemistry exam and not maths exam. Then of course you are going to perform worse. You're not going to perform good at all. But if it is a maths exam and you have prepared all the topics in maths, you will do good in any of the topics. Okay. Any questions, guys? This is all I had for today. This is all I had for the topic of cross validation. There are codes for this, which I'll probably cover some other day because I'm already very tired explaining this to you guys. So what I will do is I will maybe prepare a separate video on the codes where I will walk you through the codes, and I'll upload that video on the LMS. Okay. And if you have any doubts, we can take it up in the next class, or I'll cover that in a class only. So let me see, because we are already running very slow with the course, guys. We have lost a lot of classes. So let me see if I can cover that in a video. I'll try to explain from basics in that video so that you understand. Okay. Otherwise, we will take it in the class. But the codes will not be very difficult. It will be easy. The main crux is the concept. So please make sure you understand the concept well. So guys, I have a video which I have already recorded on the concept of cross validation. So let me play this video for you. Okay. I'll play this video. It will be a revision of whatever we have discussed so far. Okay. So just let me play this video. Just remember one thing. So this video was made for the R batch. Okay, the batch which was in R. So you will hear a few terms which is not present in Python. So you will hear, for example, min bucket. So what is this min bucket? This is nothing but min samples leaf. Okay, in R it is known as min bucket. The name of the parameter is different in R. Okay, it is min samples leaf in Python, and that same parameter is called min bucket in R. So you will hear the word min bucket there. So that is probably min samples leaf in Python. Okay, so just understand it that way. So I'll play that video now. So one of you, please tell me if you can hear the sound in the video, because sometimes people are not able to hear the sound. Just a minute, I haven't played it yet. In the previous video we talked about the disadvantages of having three sets of data set: training, validation, and test data. So the disadvantage is that when you divide your data into three parts, you really have very little data remaining to train your models, and hence the performance of the model takes a hit. The other disadvantage is your parameters are tuned based on a specific set of records which is present in the validation data. And if the validation data has, let's say, outliers, for example, the parameters might get wrongly tuned. And hence, we do not go ahead with that concept of dividing the data into three sets of training, test, and validation. So what do we do instead? We instead do a process of cross validation. So cross validation is used instead, and this is used with almost all popular algorithms. This is usually used with algorithms which are very flexible in nature. So all the non-parametric algorithms, they are very flexible in nature. They have high variance, and hence parameter tuning is mandatory for them. So cross validation is generally used for non-parametric models which have a high variance. So let us see the different methods involved in cross validation. We will talk about two methods. The first method is leave one out cross validation, or LOOCV in short, and the second method is k-fold cross validation. We will talk about the second method in a following video. So in this video, we will only talk about leave one out cross validation. So what is leave one out cross validation? This is very similar to what we just discussed, dividing the data into training, validation, and test. But instead of dividing the data, so we will still divide the data in train and test. We will still have the test data set. This is mandatory. We will still have it. So this is only the training data, and we will still have a test data. But from the training data, we will not divide it into two parts, training and validation. Instead of having two parts, training and validation, of comparable sizes, what we will do instead is, if we have n rows in the training data set, we will take n minus 1 rows. We will take n minus 1 rows, and we will train our model on this data set. And the last row, the nth row, that will become our validation data. So we will treat that as our validation data. So we will build our model on n minus 1 data points, and we will predict, or we will tune the parameters. We will decide what value of min bucket to select based on the feedback that we get from the validation data. So whichever min bucket parameter gives the best value of accuracy on the validation data, we select that. So this removes the disadvantage of not having enough records to train the model, as we have almost all but one record to train the model. But still we have the issue that what if the outlier is present in the nth row? That issue still exists. So what we do, we iterate this process again and again. So this process is iterated again and again. So for example, if this is the data, we start with
In the first iteration, we will take 1 till n minus 1 as our training data, and our validation data will be the nth row. In the second iteration, we will take 1 till, let's say, nth row except the n minus 1 row. So n minus 1th row will come here. So let's say our n is 10, we have 10 rows of data. So we will take 1 to 9 and the 10th row will be the validation. Then we will take 1, 2, 3 all the way till 10 except 9. Except 9, 9 will come here. Similarly, we will take all except 8 and 8 will come here, and this process will repeat. So ultimately you will see all the rows coming here one at a time and all the way till 1. So we will run the modeling process 10 times here, or n times, where n is the number of rows present in the data set. So that is why it is known as leave one out cross validation. Why leave one out? Because we are leaving one of the rows out as the validation data, and hence it is known as leave one out cross validation. So this removes both the disadvantages that we talked about in the previous video. It removes the disadvantages that we did not have enough records to train the model. In all these iterations, we have 9 records to train the model out of 10. So we have only excluded 1 row. So we have enough data to train the model, and it also removes the disadvantage of what if the outlier is present in the validation data. So we are keeping each row into the validation data. So even if 1 or 2 of them is an outlier, it wouldn't make much of a difference, because we are keeping each row one at a time as the data in validation data set. And the final error of the model, or the final accuracy of the model, will be taken as the average of all errors. Average of all errors that we make here. So there are 10 models. Each of the models will make some errors. We take the average of all the errors that are being made here. Similarly, accuracy also, we take the average accuracy out of all the accuracies that we get here. So this is the process of leave one out cross validation, which is beneficial because it gets rid of both the disadvantages that we talked about in the previous video. But this also suffers from one disadvantage, and which is probably why it is not used. So it has one big disadvantage which you might have noticed. So the disadvantage is that it takes a long time to run. It is time taking. Now why it is time taking? It is time taking because you are running n models. So a total of n models are being run. So imagine if you have 10,000 rows, you would be running 10,000 models, or you would be running the same model rather 10,000 times. So 10,000 iterations of the same model will be running, and obviously that will take a lot of time to run. So this is the only disadvantage of leave one out cross validation, and a big disadvantage I would say this is, and this is why it is not used in the industry. So we will see the next method of cross validation, which is k-fold cross validation, which is very popularly used, and it removes all the disadvantages that we have talked about so far. Let's talk about k-fold cross validation. Quick recap: we have seen leave one out cross validation in a previous video and the disadvantage of it. Leave one out cross validation, what do we do there? We take n minus 1 data points as the training data, and the nth data point we take that as the validation data. This is one of the iterations, and we repeat the iteration by changing the data which goes into the validation data. So we take each individual row, and one at a time we take that as the validation data. So we run n different iterations. So n iterations of the models is run, and finally we aggregate their output. So this is the final error. This is the final error that we take as the leave one out cross validation error. Now this has a disadvantage that we are running n iterations of the model. So imagine if you have 10,000 rows in your data, you would be running 10,000 different iterations. So this would be painfully slow, and hence we cannot proceed with leave one out cross validation. So an alternative to that is k-fold cross validation, which is very popularly used. So all non-parametric models, in fact, they almost always go through a process of k-fold cross validation. So this can be used to tune the parameters also. So for example, we were talking about the min bucket parameter or any other parameter in any algorithm. We can always tune the parameters. Tune the parameters is used to denote finding the right value of the parameter, which neither underfits the data nor overfits the test data. So that can be done using k-fold cross validation. So let us see what is k-fold cross validation. So if we have n data points, let's say we have n data points in our training data. So we will still have our test data, which is a general process we'll always follow. We'll always have a test data set. Now from the training data, what do we do here? We divide our data sets into k folds. Folds means k parts. We divide our training data set into k parts. K is usually taken to be 5 or 10. So let's say we are assuming k to be 5 here. So I will divide my n rows into 5 parts. Let me call it fold 1, fold 2, fold 3, fold 4, and fold 5. And almost always these parts are comparable, they are equal. So if you have n points, if you have 100 points, you will have 20 in each of them. So these are the 5 folds that we have now, if you have taken k to be 5. Now what do? We start with some iterations. So in the first iteration, we take the first 4 folds as our validation data, as our training data, sorry. So let me write here training and validation. So we will take fold 1, fold 2, 3, and 4 as our training data, and the 5th fold will be the validation data set. So we will build a model on this data and allow it to predict on the validation data. Or if we are tuning our parameters, we will train our model on this data and we will find out the best value of min bucket, which gives the best accuracy on this 5th fold. Now we repeat the process. So we will have F1, F2, F3, and F5 here, and we will take F4 as the validation data. Similarly, all possible iterations we will do, and you will see that we will have a total of 5 iterations. So F4, we will have F3 and F2, and finally we will have F1. And here we will have and finally F2, F3, F4, and F5. So these are the different iterations we will run. Now, if you look this carefully, you will see that we are running only 5 number of times, only 5 iterations we are doing. So this is not as bad as leave one out cross validation, where we were running it n number of times. So here we are running only 5 times, and your final cross validation error, your cross validation error will be 1 by 5 of all the errors that the model makes. So you take the average of the error. Now this can be used for parameter tuning. You can tune your parameters based on what is the parameter which in general gives the best score on the validation data. So for each value, so let's say we are talking about a parameter. Let's say this is the parameter that we are talking about. So for each fold or for each iteration from here, we will plot the accuracy. So let's say this is the accuracy on y-axis. So for the first iteration, let's say this is how it looks like. This is the accuracy for the first iteration. So accuracy on first fold, let's say. So if you see the parameter when it is small, when the parameter is small, your model overfits. This is where overfitting happens, and this is where underfitting happens. So if the parameter value is small, your model overfits. This is the best. This is the sweet spot. Similarly, we will do for the other folds also. This is on F1. So this is for this particular iteration I have drawn. Similarly, for other iterations, you can have similar graphs. Let's say this is for F2. F2. So for this iteration, I have drawn the green one. Then you can have others as well. You can have, let's say, one more. This blue one is for F3. Let's say pink one is for F4, and you will have the last one, which is for F5. So let's say this is for F5. So finally you aggregate the results, and on an average you will draw a line which will be the average of all of them. So let's say this is the average of all of them. This is the average line, and you will find out what value of parameter is best for this average. So this is the parameter value. This is the parameter value which is best for all of them. So this is the parameter that you will finally select for your model. So your model will be trained based on this particular value of parameter, and using that model you will predict on your test data. So this is the process of k-fold cross-validation. Quick recap. In k-fold cross-validation, we divide our data into k-folds. These k-folds are generally equal in size. So if you have 100 rows of data and you divide your data into 5 folds, you will have 20 data points in each of the folds. You take k minus 1 folds as your training data and the kth fold as your validation data. And you repeat this process until each fold becomes your validation data. So you will see that you will be performing k iterations in total, and finally you aggregate the results. So the accuracy, the error, the overall error will be average of errors made by all the 5 iterations or all the k iterations. K-fold cross-validation can be used for parameter tuning. So what we do is we plot the accuracy with respect to different values of parameter, and finally we average out the result, and for the average result, whichever parameter works out to be the best is finally selected for the model. In the next video, we will see how to implement k-fold cross-validation in R.
Guys, can you hear me now? Okay. So was it clear now? So I'll share that video also separately on the LMS. So that also explains the same that we have discussed today. I'll also share a few reading material. So please go through it, and I'm sure you will understand. Okay. So any doubts? Do you have any doubts? So that video pretty much did a revision of whatever we have covered today. So any questions do you have? This is all I had for today. We will see the codes. I'll either share it via the LMS in a video, or we will take it up in the next class. But for now, I'm already tired, so I'm not able to speak. My voice is not coming out now. Okay. So this is a very difficult concept. So in every batch, I find people having trouble to understand cross validation, which is why. But none of the other batches have had all these videos that I shared with you. And the LMS, you are the first batch to receive the LMS. Okay. So actually, the LMS was not planned for you guys also. It just happened. I was testing the LMS, and I thought while I'm testing, let me anyways have it open to you guys. But the LMS was not planned for you. Okay, guys, are you able to hear me? Okay, Anupam, I think there's some issue at your end then. So any questions do you have, guys?